All right, subscribers, welcome back to another episode of Science with Surback. Today we're going to talk about section 9.1, which deals with the covalent bonds. The objectives for this section is 1. Apply the octet rule to atoms that bond covalently. 2. Describe the formation of a single, double, and triple covalent bonds. 3. Compare and contrast sigma and pi bonds. And 4. Relate the strength of covalent bonds to bond strength and bond dissociation energy. So we start out here with a real brief review of bonding. And the whole goal of bonding is to get that perfect octet. And in our last couple sections, we talked about atoms losing or gaining, those are ions, to achieve this perfect octet. Now, what we can also do is share these electrons. So that's what we're going to be interested in this particular few sections when we discuss our covalent bonds. So let's go jump right into it about what covalent bonds actually are. So covalent bonds are chemical bonds that result from sharing electrons, okay? So as a result, because they share those particular electrons, both of those atoms involved in that sharing process complete the outer energy level or have electrons that fill that outer energy level. Now, most of the time, these elements are going to be on that right-hand side of the periodic table, are non-metals, and it's a relatively small group that goes into these covalent bonds, and we'll talk about that here in a second. Now, as we talk about covalent bonds, we can also bring up another topic or another definition, and that is a molecule. So a molecule is when we have a covalently bonded chemical. Now, you've probably heard of these in biology before. They include things like DNA, synthetic fibers, and simple sugars. Again, molecules is just saying, okay, well, specifically, these chemicals are bonded covalently. So that's something to keep in mind as we go through this process. Now, what we have to consider when we share these electrons is our repulsive and attractive forces. So you have to remember, around the outside of an atom is those electrons. And so as they come closer and closer and closer together, they are going to have those electrons clouds get closer. Now, if they get too close, then they repel, right? Same charge repels, but they need to be close enough where they can share those electrons. So they have to find, the atoms have to find this happy medium mix where they can be close enough to share the electrons, yet not too close to repel from those electron clouds. So it's something that has to be considered as covalent bonding is done. Now, what we can talk about and what we usually do to describe our covalent bonds is our Lewis structures, okay? So our Lewis structures are a visual representation that we can see what happens with our valence electrons. So let's take hydrochloric acid and let's draw that Lewis structure. So the easiest way to draw that Lewis structure is start out with that symbol H. And remember from previous sections, H, hydrogen, has one valence electron. Now Cl, we'll draw Cl, the symbol here, and Cl has 7 valence electrons. So I'll represent those by our dots, and then we'll go from here. Now, what I'm going to do is I'm going to connect the lone electrons, and as I connect them, that is going to become one straight line that represents a covalent bond. So when we draw the Lewis structure for HCl, it would look like this. Now, this one single line here represents 2 electrons that are shared between both hydrogen and the chloride, or our chlorine in this case here. Okay, so now we can talk about the different types of bonds that form with our covalent bonds. So that was just a real quick intro to covalent bonds. But we can talk about the three different types of bonds that we have, and the first of which is single bonds. So again, the best way to show this here is through our Lewis structures. And so we just got done drawing Cl. And so if we draw the Lewis structure for Cl, it would look like this. Now, because Cl is what we call diatomic, we would have to represent our other chlorine like this. Now, what we would do is we circle the lone electrons, and so when we would draw the Cl molecule, it would look as follows. We can do the same thing with CH4. The one thing that I want to emphasize is that, hey, this is one pair of electrons or two electrons. So one pair, or two electrons. Okay, so one line represents two electrons. Now CH4. Carbon has 4 valence electrons. It would look like this. Hydrogen has 1 valence electron, but we have 4 of those hydrogens. And so when we would go to draw the Lewis structure, it would look like this. And we would more clearly represent it with that one single bond to represent a single line. So a single line represents a single bond. Now, as we talk about our covalent bonds, we can bring up this concept of a sigma bond. So essentially a sigma bond is the direct overlap of orbitals where those electrons are shared. So when this happens here, what you're doing is you're creating a region. You created a region where those electrons can be shared. Now, I like to think of sigma bonds as a Venn diagram. So if we draw a Venn diagram here, and I'm just going to represent it by 2 circles, you always have that area of overlap. Now, that area of overlap here, this is where electrons are shared, and we can also call this our sigma bond. And again, it's just representing that direct overlap where electrons can be shared. Okay, so now we can move on to our double and triple bonds. And so if we go through the same process, there's some particular molecules that can't form that perfect octet with the electrons that are given by only forming single bonds. So if we have here our oxygen example, oxygen, remember, has 6 valence electrons. And because it's diatomic, I'm going to draw the same molecule here. And we need to connect our singles. Nobody likes to dance alone, so we will connect these single electrons. And this would be represented as follows on our Lewis diagram. Now, couple things here. Each line represents 2 electrons. So in between these 2 molecules, there is 4 electrons shared between the oxygens. Now CO2, I'm not going to take the time to draw the electron dot diagrams. I'm just going to go ahead and show you what CO2's Lewis structure would look like. And again, carbon has 2 double bonds. So again, carbon is sharing a total of 4 electrons, and you can count up 2, 4, 6, 8. There is 8 electrons around those carbon. Now we'll get more practice with this, so don't get too caught up in those Lewis structures at this point. All right, so a triple bond would come through in a similar way. So triple bond, there's 3 pairs of electrons, which we represent by 3 lines. And now we can show that with our nitrogen molecule. And nitrogen, remember, has 5 valence electrons, so I'll put 5 dots around our particular atoms. And again, we connect the lone pairs, the lone electrons, and everything that I circle becomes a bond in between those nitrogens. So we would get something that looks like this. Now, our ethane would look like this. And a triple bond is, again, just represented by 3 lines. Each line represents 2 electrons, so there's 6 electrons shared here. Now, when we have a double or a triple bond, we can also talk about this other item, which is a pi bond. So essentially with a pi bond, you have, it says by definition, parallel orbitals overlap. Now, what this means for us, if we think about our p orbital, which again was this dumbbell shape, we would have one p orbital, and as atoms get closer and closer together, they would have this second p orbital. And this second p orbital, this overlap here that I'm pointing to with an arrow, is a pi bond. And that would be, again, our pi bond. Now, we've learned the basics of our covalent bonds. We've talked about single, double, and triple bonds. I want to go into a little bit details about what those bonds represent and what we can really interpret by single, double, and triple bonds. So we start out here and we start talking about diatomic molecules. You need to memorize this list, okay? Anytime you see these alone, they need to be written as H2, not just H. So if you see hydrogen by itself, it needs to be H2. And same thing all the way down this list. Again, these things are more stable because they form those covalent bonds by sharing electrons between those 2 particular atoms. Now, our last thing that we're going to talk about here is what happens with our bond length and our bond strength, okay? So, key thing here, as bond length increases, strength decreases, okay? So, our fluorine has a single bond. It has the longest. Our nitrogen has a triple bond, and it has the shortest bond length. So, right here, nitrogen here would be the strongest covalent bond because it's triple, and fluorine, because it's only a single covalent bond, this would be the weakest. And then obviously smushed in between would be that double bond, okay? Now, how we can represent that is actual bond dissociation energy, which bond dissociation energy is just saying the energy required to break a bond apart. Now, the shorter the bond, the greater the energy required to break it apart. And so just as a reminder here, fluorine has a single covalent bond, and nitrogen has a triple covalent bond. So a single covalent bond has much less energy needed to break it apart than a triple covalent bond, which makes more sense. The more items, the more things that are shared, the stronger it is, the more energy it takes to break it apart. Okay, so our last thing here is this. As you break those bonds apart, sometimes it either requires or gives off energy. So if it requires energy, it's endothermic, and if it gives off energy as those bonds are breaking, you have that exothermic, okay? So all of this plays a role into chemical reactions, which we'll get into more and more as we finish up this year. All right, so that is everything from section 1. Hope you have enjoyed this episode, and as always, if you haven't done so already, make sure you subscribe.